Hi everyone, my name is Marius Millea. I'm a postdoc at UC Berkeley, and today I want to tell you about what my vision is for CMB lensing in the 2020s. The main points I want to get across are basically that at this point CMB equals CMB lensing. Lensing touches almost all aspects of observations, and our analysis techniques for dealing with lensing are basically changing right now. So I want to tell you about the old and the new. Now, this talk is both very general and broad at times, and I hope useful to anyone, and at other times gets quite technical and may be useful to someone that is actually working on lensing or may work with CMB lensing data products, even if they don't work on CMB lensing. To start, a little demo to get everyone on the same page. Here's a patch of simulated CMB temperature, about 10 degrees on a side, and I'm going to lens it by this deflection field that you see here. Now, these deflections track the total deflection the photons have undergone since the last scattering surface. And it turns out that under the so-called Born approximation, this can be written as the gradient of a scalar potential. And usually we just talk about this potential, phi, and its power spectra, and so on. And I'll try to use this color scheme to remind you when we're looking at phi in this talk. So here's the unlensed CMB again, and now I'm lensing it. You can see the deflections are small. They're about 1 arc minute on average, but they're coherent across degree scales. And here's the difference between the two and on a blown up color scale. The main thing to take from this is that they're mainly small scale differences and that the power that is added is highly non-Gaussian. So what about polarization? Here's a simulated polarization field, which is just a headless vector field. The lensing works exactly the same. You're just looking at it at a displaced position. But polarization is unique because you can decompose it into two components, the so-called E modes and the B modes. Now these are patterns on the sky, and they're defined basically by how they behave when you mirror them. So the E modes stay exactly the same, whereas the B modes rotate by 90 degrees. And what happens when you lens, say, an E mode? So here's an E mode, and I've lensed it, I've sheared it, and now let's do the mirror test. And you can see it's no longer a pure E mode. It's also not a pure B mode. It doesn't rotate by 90 degrees. So lensing basically mixes E and B modes together in either direction. So now going back to the picture of the CMB lensing, I've decomposed it now. On the left are just the E mode part, and on the right are the B modes. You can see the B modes are way smaller because it turns out B modes can only be generated by tensor perturbations during inflation. And I've put in a level here that is about the level we think we can achieve in future searches, but we don't even know for sure that this is there. Here's what happens when you lens this now. The E modes sort of look like before, but the B modes you can really see when you look at just this channel that you go from almost nothing to a huge amount of power generated. And usually we plot the local intensity of the E and B modes. So like a hotspot in B is a swirly pattern, or hotspot in E are the pluses and circles. And if you look at this now, you can also see that the B modes that are added are also highly non-Gaussian. And this is key in searching for the lensing and reconstructing it. A little more quantitatively, here's the power spectra of the maps that we were just looking at, overlaid with some of the most recent data. You can see that the T and the E modes have been measured quite well. There is some room for improvement, and especially at small scales where the lensing is most important. And the B modes are sort of just starting to be measured really well. And the better we do at this, the more we can hope to unearth that primordial signal that sits below them, as well as better reconstructing the lensing potential. Because again, the B mode channel is such a clean channel. Almost anything we see there we know is lensing. The lensing potential power spectra you see on the right has been reconstructed from many experiments. And its power spectrum contains a wealth of information about the late time structure formation of the universe and of its expansion history. And in cross correlation with other probes, we can also infer a number of astrophysical constraints as well. So how do we measure these power spectra from data? Well, as you might have guessed from the introduction, it's all about searching for non-Gaussianity. So first, what is a Gaussian random field? If we work in the flat sky approximation on a small enough patch of sky, that'll make understanding this easier. Basically, a Gaussian random field has the property that you just take the map, you take the 2D Fourier transform of it, and then you ask what's the expectation value of products of different modes averaged over many realizations. And if you're looking at the exact same L mode, then you get back the 2D CMB power spectrum. And if you're looking at two different modes that differ by a big L, then you just get 0. Lensed fields, which are non-Gaussian, you won't necessarily get 0, and in fact, it turns out you get something which is proportional exactly to the lensing potential phi evaluated at that big L. Now, this immediately opens up a way to compute an estimate of phi because even within one realization of the data, there's many pairs of L modes that differ by a big L. And if you just average over all of those, you will converge slowly towards the lensing potential phi at that big L. Once you have phi, you can just take its power spectrum and you get back an estimate, which on average gives you back the theory spectrum up to some normalization AL, plus some noise biases NLs, all of which you have to compute and subtract out. Now, despite being very simple and widely used, this estimator does leave some information on the table. In particular, there's a second order term there, phi squared, which usually is just calibrated out as a bias in the N1 term, but in theory there's information there. And it hasn't used any of the higher order point functions, only the 2-point function, but there's information in theory in the 3, 4, and higher order moments of the data. Now, it turns out that this missing information doesn't matter too much as long as your noise levels are kind of high, but we are basically just now crossing the threshold where these extra terms do begin to matter and you can do better than the quadratic estimate. This has been known for almost 20 years. Here's a plot, for example, showing you this. The first curve there is the quadratic estimator noise spectrum. It's basically the sum of all those noise terms you saw on the previous slide. And there's another curve, which is almost an order of magnitude lower noise, which is coming from so-called iterating the quadratic estimator, something which I'll argue in a little bit more precisely can be called the marginal map maximum a posteriori estimate. So you can do much better, and potentially even that's not quite within reach of the true Fisher information, so maybe you can do even better. Now, these curves in this paper basically function off of their forecasts or their highly simplified analyses. What's missing, and what now, almost 20 years later, we're really turning to, is asking, how do we actually do this to real data that has all the complexities that come along with real data? People have tried sort of a number of different things over the last few years. These include things like machine learning, basically training a network to extract this information from the data in a nonlinear way. This achieves noise levels that are comparable to that iterative forecast, but basically, I think, suffers from the same challenges in estimating parameters from these maps, which I'll discuss in a bit. People have tried to just write down better estimators, but the issue there is that you only get simple analytic formulas in various asymptotic limits. Here, we want something that basically works everywhere. There's different pieces of the quadratic estimator analysis that have been optimized. For example, the optimal filtering in the paper that you see here. But again, that's just a piece of the whole thing. The one really guaranteed way to get the optimal answer is to basically do the full Bayesian solution, in which case you're guaranteed to be optimal, but it can be quite computationally hard. So what I want to show you is basically that we can solve that computational challenge. Bayesian lensing is conceptually super straightforward. All you need is a data model and a set of priors. Here is kind of a simplified version, and I'll show you something more complex in a few slides. But here, we just take that the data is the lensed CMB. So L is a lensing operator, which depends on phi. It multiplies the unlensed CMBF, and then there's a noise term. The priors are that the CMB is a Gaussian random field with covariance given by CF. That's just the thing we saw on the other slide. Phi has its own covariance. N is the noise covariance that you put in from your instrument. And these things might all depend on some parameters theta that could be cosmological parameters or even just directly the theory spectra themselves. Now, once you have this, then it's totally straightforward to get the posterior joint over all these variables. And it's right here. It's basically just 3 Gaussians, the data compared to the data model, and then the priors on F and on phi. It turns out you can analytically marginalize that expression over F and arrive at the so-called marginal posterior. And here it's slightly simpler because, well, there's only 2 Gaussians, but there's an added complexity because one of their covariances is now much more complicated. It's this CD thing that you see there, which turns out to not be sparse in any simple basis and actually make computing the value of this posterior essentially impossible, although you can still compute its gradients. Using these gradients, you can maximize these functions and compute maximum a posteriori estimates either in the marginal or the joint case, both of which are better reconstructions than the quadratic estimate. This is basically an iterative gradient descent-like procedure, and it turns out that the first step of this for the marginal map case basically is the quadratic estimate, and so that's the reason for calling the iterative quadratic estimate more precisely the marginal map. In either case, you have to pick a fiducial set of cosmological parameters, theta fid, to do the maximization at, and this is kind of a first sign that something is weird, since that's the thing you would then try to get out of these estimates in the end. So it's kind of circular. In any case, on the left you see images of these different estimators. This is actually from real South Pole telescope data, and I'll tell you more about that in a couple of slides. But here you can sort of qualitatively see the difference between the estimators. Now, the quadratic estimator can be properly normalized analytically, basically, and that's been done here, and that's the reason you see more structure at small scales. The other estimates, you can't do this. You just get what comes out of the maximizer. And what comes out is something more or less like a Wiener filter, where basically scales that are low signal to noise, here small scales, are suppressed. The joint map additionally has a mean field feature in it, which you can kind of see in the image, but in terms of the power spectrum, it's mainly just the very largest scales. Otherwise, the joint and marginal maps are almost identical. Now, the fact that you can't properly normalize these map estimates is actually a big deal, because it means you don't have something that you can compare to theory. And you can imagine doing this with Monte Carlo or something like this, but this is now a much more expensive thing that you're Monte Carloing. It will depend on the input theta fiducial that you're trying to estimate in the end. And unlike the quadratic estimate case, where there's tricks where you can sort of take that out, there's tricks to better calculate noise biases and so forth. You don't have any of that in this map case. And so for this reason, I just don't think this is the right path to try to get power spectral and cosmological parameters out of the Bayesian posterior. Instead, what I think is the right way is to go back and we'll use the one which is easier to compute, the joint posterior. And instead of maximizing, what we actually want to do is marginalize. We marginalize over the parameters that we don't care about, say the unlensed CMB and the phi maps. What we actually care about are their power spectra, or maybe the parameters that control their power spectra. And so marginalizing, we just get this marginal posterior on just those parameters. And by virtue of sort of Bayesian statistics, this is guaranteed to have extracted all the information that was available given our model in priors. But the hard part is this marginalization, because this is like a million or more dimensions that we're trying to marginalize. These are the maps, the value in every pixel. And so something, say, like Metropolis Hastings that people may be familiar with will never work because of the curse of dimensionality. They'll never random walk around this space fast enough. We need gradient information. And basically, MC with gradient information is Hamiltonian Monte Carlo, which does actually work quite well. But one thing we do need to do, though, is actually tweak a little bit this posterior to make it more amenable for sampling. In particular, we switch from sampling in terms of the unlensed field and phi to sampling in terms of something like the lensed field and phi. And so that just switches the posterior like you see there, introducing an inverse lensing operation in place of a forward lensing one, and introducing a determinant. And both of these are actually key challenges, because how do you take now a gradient through inverse lensing, and how do you compute the determinant of lensing? We solved this problem by developing this algorithm called LensFlow, which works something like this. So in traditional lensing, you evaluate the unlensed field at a displaced position, and then maybe you tailor expand around that. With LensFlow, you introduce this auxiliary time variable t, and at t equals 0, you have the unlensed field. At t equals 1, you have the lensed field. And it turns out that you can write down an ordinary differential equation that you see there that connects t equals 0 to 1. So to lens the field, you just solve the ODE forward in time, and to unlens it exactly, you solve it backward in time. This is kind of like smoothly connecting the unlensed pixel values to the lensed pixel values with a series of layers that correspond to each step in the ODE solver. And so you can imagine that to get these gradients through inverse lensing that we need, you can do something kind of like in machine learning, like backpropagation through these layers. But actually you can do something even better and more efficient, which is that there's another ODE you can write down that computes these gradients for you without explicitly doing the backpropagation. This is basically the same insight that has led to all of the excitement in neural ODEs in machine learning. And another reason for their popularity there also is that neural ODEs or other flows like normalizing flows let you compute determinants of these operations easily. And we have the exact same thing with LensFlow. We can compute that determinant term, which is the final piece that we need to compute that full posterior, and basically lets us do the sampling. To show you how this really works, let me present some preliminary results from an analysis I'm working on in the South Pole Telescope collaboration. This is using 100 square degrees of polarization data, basically the deepest taken to date at these angular scales relevant for lensing. And this is the work of a big collaboration, and in particular, I want to thank the people that you see listed here that have helped on this analysis. One of the things that sometimes is a perception of Bayesian analyses is that, okay, you can do it on simulations, but on real data, it's too hard. And actually, I think if anything here, I found sort of the opposite. There's a large amount of real data systematics modeling that you can do much easier than would otherwise be possible. So here's the data model that we use for this analysis. Like before, there's lensing and there's the unlensed field. There's noise. Now we also include a few extra things. For example, we have temperature to polarization leakage templates with coefficients that are free parameters. There's a beam and transfer function that don't necessarily need to be isotropic. There's a global polarization rotation corresponding to the calibration of the instrument, as well as a polarization calibration. And we have pixel masks and Fourier masks that we can apply. And again, from this, it's totally straightforward to write down that posterior and then take the gradients, do the HMC, and the whole thing. Here I'm showing you the value of some quantities of interest at each step in the chain. There's some of the systematics parameters from the last slide. There's the main cosmological parameter of interest, A phi, the amplitude of the lensing potential that you see in the top left. And then I'm showing you about 20 of the 200,000 Fourier modes that are actually sampled alongside all of these on the right. The main thing to look at here is just checking for convergence, which indeed does look good. For reference, we're running about 16 chains in parallel on GPU, and what you see in front of you here took about 4 wall hours. Parameter constraints come from histogramming up those samples, like you see here for A phi and for the systematics parameters. And so this is implicitly marginalized over those 200,000 other parameters, which was the main goal in the first place. And one thing that's pretty cool is these systematics are now on totally equal footing with everything else. You can look at the cross correlation between this and the cosmology. It's totally straightforward how this folds into the final error budget. And this is different than previous analyses where sometimes you have sort of the main analysis and then you just fudge the systematics back and forth a bit, see how they impact the final answer, and then kind of guess what the final budget is in terms of the systematic error. And sometimes actually you just straight up do better. So if you look, for example, at the polarization calibration coefficient, in previous SPT analyses, this actually contributed half of a sigma to the final cosmological uncertainty. And the reason for this was actually because to have done the analysis better and reduce this was just too hard. It would have corresponded to something known as more or less bias hardening. Here, you just get that for free, since the Bayesian thing is just implicitly doing the best thing anyway. And you can see that the error is actually basically reduced to almost 0 from that original half of a sigma. Finally, we want to compare the Bayesian and the QE results to see if we're in this regime where the Bayesian is doing better. And indeed, that is what we find. It's about 20% tighter error bars than the quadratic estimate case. So this represents the first time that cosmological information was extracted from CMB lensing using one of these more optimal methods. And this will only get better with time as noise levels get lower and lower. You saw on one of those first slides, the noise level could be almost an order of magnitude below the quadratic estimator case, and that will impact here as well as in cross correlation or in delensing. So having seen that it basically works, I now want to give you sort of a whirlwind tour of what we're planning on doing with Bayesian lensing in the future. And I do think that it'll pave the way to solve some of the tough analysis challenges that we'll be facing, similar to how well it handled the systematics in the previous case. So one thing we worry about is foreground contamination. And in polarization, where most of the gains are going to come from, the main foreground we worry about are unresolved point sources. Now, being able to just model these point sources is actually not quite enough for the Bayesian analysis. We actually have to have a model for their prior distribution. But because these sources are so simple in a lot of regimes, sometimes they're just Poisson sampling at random locations on the sky, you can actually get analytic formulas for their prior and then stick that in the posterior and do everything else self-consistently. So if we find that these are important and we need to model them, we have a way to do it. In some cases, we don't have analytic models or there's no hope, for example, galactic dust. But here, actually, machine learning models can really help us because they can be trained to produce images of galactic dust, like you see here, in which case they are essentially trained to understand the prior distribution of dust. And also we have gradients via backpropagation, which are all the ingredients we need to stick them in the posterior and sample. Here's a small movie showing you an early prototype of some of this sampling, which basically works. Finally, one thing I'm quite excited about is the possibility of joint band power estimation, meaning instead of estimating just a single parameter like A phi, we can estimate the full band powers of phi and perhaps the D-lensed E and the B modes. That involves doing the integral that you see here, and if you do it with our procedure, it just gets kind of heavy, and there's all these new parameters to sample over. And so with CellJack, I've been looking at ways to approximate this integral. and get something which is still quite good. Now the key is that because we have the chains, we can actually compute the exact Fisher information in these band powers and compare to our more approximate estimate. On the left here, you see, for example, the black line is this Fisher information, and we have an estimator, which in this case gets within about 10% of the Fisher information. And so it's quite good, but is an order of magnitude faster. The final output then are band powers of phi, d-lensed E, as well as the covariance between them, all having self-consistently taken into account the lensing and the de-lensing. So this I'm quite excited about, and stay tuned for this work. To conclude, in the near term, we will still see results from the quadratic estimate, including using interesting tweaks that people have developed, which I've unfortunately not had time to mention. But ultimately, lower noise levels will demand that we switch to something more sophisticated, and there I hope I've convinced you the Bayesian solution is a promising path forward. Finally, I'll just mention, check out our code, cmbLensing.jl, which computes any of the estimates or of the sampling that I've discussed, and I think does some cool things with GPU, automatic differentiation, and various other technologies. If you've been meaning to have an excuse to try it out, this week while I'm on the Cosmology from Home Slack and can answer questions could be a good one. So, thank you.